Welcome to Tech Girl Kannada YouTube channel. For Module 4 Input Output Organization. There are a number of input or output devices that can be connected to a computer. The input may be from a keyboard, a sensor, switch, mouse, etc. Similarly, output may be a speaker, monitor, printer, or a digital display, etc. These variety of I/O devices exchange information in a varied format, having different word length, transfer speed is different, but are connected to the same system and exchange information with the computer. Computer must be capable of handling these wide varieties of devices. Accessing the I/O devices. A single bus structure can be used for connecting I/O devices to the computer. A simple arrangement of connecting set of I/O devices to the memory and processor by means of system bus is as shown in the figure. Such an arrangement is called as single bus organization. Bus I/O device 1, processor, memory, I/O device N. Single bus structure. The single bus organization consists of memory, processor, system bus, I/O devices. The system bus consists of three types of buses: address bus, unidirectional; data bus, bidirectional; control bus, bidirectional. The system bus enables all the devices connected to it to involve in the data transfer operation. The system bus establishes data communication between I/O device and the processor. Each I/O device is assigned to a unique set of address. When processor places an address on the address lines, the intended device responds to the command. The processor requests either to read or write operation. The requested data are transferred over the data lines. Steps for input operation. The address bus of system bus holds the address of the input device. The control unit of CPU generates IORD control signal. When this control signal is activated, the processor reads the data from the input device, data N, into the CPU register. Steps for output operations. The address bus of system bus holds the address of the output device. The control unit of CPU generates IOWR control signal. When this control signal is enabled, CPU transfers the data from the processor register to the output device, data out. There are two schemes available to connect I/O devices to CPU. Memory mapped I/O. In this technique, both memory and I/O devices use the common bus to transfer the data to CPU. Same address space is used for both memory and I/O interface. They have only one set of data, read and write signals. All memory related instructions are used for data transfer between I/O and the processor, CPU, memory devices. Memory mapped I/O. In case of memory mapped I/O, input operation can be implemented as move data in or not source destination. The instruction sends the content of location data in to register or not. Similarly, output can be implemented as move or data out, source destination. Similarly, this is done. The data is written from R0 to data out. Location. Address of the output buffer. I/O mapped I/O. In this technique, a separate bus is used for I/O devices and memory to transfer the data to CPU. Address space for a memory and I/O devices are different. Hence, two sets of instructions are used for data transfer. One set for memory operations and another set for IO operations. Whole address space is available for the program. Example -in ALDX IO mapped IO. In ALDX. Here, memory mapped and the IO mapped IO. Memory and IO share the entire address range of the processor. Processor provides separate address range for memory and IO. Processor provides more address lines for the accessing memory, less addressing lines for the accessing IO. More decoding is required, less decoding is required. Memory control signals used to control read and write operations. IO control signals are used to control read and write IO operations. IO interface. The hardware arrangement of connecting input device to the system bus is as shown in the figure. Bus, address line, data line, control lines, address decoder, control circuits, data and status registers. IO interface. Address decoder, control circuits, data and status registers. Input device. This hardware arrangement is called as IO interface. The IO interface consists of three functional devices, namely address decoder. Its function is to decode the address in order to recognize the input device whose address is available on the unidirectional address bus. The recognition of the input device is done first, then the control and data registers become active. The unidirectional address bus of system bus is connected to input of the address decoder as shown in the figure. Control circuit. The control bus of the system bus is connected to the control circuit as shown in the figure. The process sends commands to the IO system through the control bus. It controls the read and write operations with respect to IO device. Status register specifies type of operation. Either read or write operation to be performed on the IO device specifies the position of the operation. Data registers. The data bus carries the data from the IO and this devices to or from the processor. The data bus is connected to the bus status register. The data register stores the data read from input device or the data to be written onto output device. There are two types: data in, input buffer associated with keyboard; data out, output data buffer of display or printer. Data buffering is an essential task of an IO interface. Data transfer rates of processor and memory are high when compared with the IO devices, hence the data are buffered at the IO interface circuit and then forwarded to output device or forwarded to processor in case of input devices. Input device data in buffer, processor data out buffer, output device. Input and output registers. Various registers in keyboard display devices: data in, data out, status, control. Data in, data out, DIRQ, KIRQ, S out, as seen, done, can. Data in register is a part of an input device It is used to store the ASCII characters read from the keyboard. Data out register is a part of output device. It is used to store the ASCII characters to display on the output device. Status register stores the status of working of I/O devices. SIN flag. This flag is set to 1 when data in buffer contains the data from the keyboard. This flag is set to 0 after the data is passed from data in buffer to the processor. SOut flag. This flag is set to 1 when data out buffer is empty and the data can be added to it by processor. The flag is set to 0 when data out buffer has the data to be displayed. KIRQ keyboard interrupt request. By setting this flag to 1, keyboard requests the processor to obtain its service and an interrupt is sent to this DIRQ display interrupt request. The output device requests the processor to obtain its service for output operation by activating this flag to 1. Control registers can control register keyboard enable then display enable enables the keyboard for input operation, enables the device for input operation. Output operation. Program controlled I/O. This technique CPU is responsible for executing data from the memory for output and storing data in memory for executing of programmed I/O. Drawback of the programmed I/O was that the CPU has to monitor the units all the times when the program is executing. Thus, the CPU stays in a program loop until the I/O unit indicates that it is ready for data transfer. This is a time consuming process and the CPU time is wasted a lot in keeping an eye to the executing of the program. It is the process of controlling the input and the output operations by executing two sets of instructions, one set for input operation and the next set for output operation. The program checks the status of I/O register and reads or displays data. Here are the I/O operation is controlled by program. Wait k test bit 0 status checks SIN branch equals to 0 wait k move data in RO. Read character code to read a character from data into R0. This code checks the SN flag and if it is set to 0, if no characters in the data in buffer, then move back to wait k label. This loop continues until SN flag is set to 1. When SN is 1, data is moved from the data into R0 register, thus the program continuously checks for the input operation. Similarly, code for output operation test bit 0 status wait D branch 0 then move R0 checks SOut flag sends character for display. The code checks the SOut flag and it is set to 1 if no characters are data out buffer. Then move back to wait k label. This loop continues until SOut flag is set to 0. Data is moved from are not registered to the data out. Then illustrate a program that reads one line from the keyboard, stores in a memory buffer, and echoes it back to the memory display in an I/O interfaces. Wait K, wait D, wait keyboard and wait display. Move test bit branch. These are all are available. The program that reads one line from the keyboard, stores it in memory buffer, and echoes it back to the display. Interrupt is an event which suspends the execution of one program and begins the execution of another program. If a program controlled I/O, a program should continuously check whether the I/O device is free. By this continuous checking of the processor execution time will be wasted. It can be avoided by I/O device sending an interrupt to the process when I/O device is free. The interrupt invokes a subroutine called interrupt service routine (ISR), which resolves the cause of interrupt. The occurrence of the interrupt causes the processor to transfer the execution control from user program to ISR. Interrupt occurs here, program 1 to ISR. The following steps takes place when the interrupt related instruction is executed. Suspends the execution of the current instruction I, transfer the execution control to subprogram from the main program, increments the contents of PC by 4 memory location, it decrements the SP by 4 memory locations, pushes the contents of PC into the stack, segments memory whose address is stored in SP, loads PC with the address of the first instruction of the subprogram. Following steps takes place when return instruction is executed in ISR. It transfers the execution control from ISR to user program, retrieves the content of stack memory location, addresses stored in SP into the PC, to retrieving the return address from stack memory location into the PC, increments the content of SP by 4 memory location. Interrupt latency or interrupt response time is the delay between the time taken for receiving an interrupt request and start execution of the ISR. Generally, the long interrupt latency is unacceptable. Interrupt hardware. The external device I/O device sends interrupt request to the processor by activating a bus line and called as interrupt request line. All IQ device uses the same single interrupt request line. One end of this interrupt request line is connected to input power supply by means of register. The another end of the interrupt request line is connected to the entire interrupt request signal of processor as shown in the figure. Processor interrupt request line int R1, int R2, int Rn, int R, RV or power supply and the processor. The I/O device is connected to the interrupt request lines by means of switches, which is grounded as shown in the figure. When all the switches are open, the voltage drop and interrupt request line is equal to the VDD and int R value of the process is 0. The state is called as inactive state of the interrupt request line. The I/O device interrupts the processor by closing its switch. When switch is closed, the voltage drop on the interrupt request line is found to be 0. As the switch is grounded, hence int R equals to 0 and int R equals to 1. The signal on the interrupt request line is logical or of requests from the several IO devices. Therefore, intar equals to intar1 and plus intar2 plus intar n, enabling and disabling the interrupts. The arrival of interrupt requests from the external devices or from within a process causes the suspension of ongoing execution and start the execution of another program. Interrupt arises at any time, it alters the sequence of execution. Hence, the interrupt is to be executed must be selected carefully. All operators can enable and disable interruptions as desired. When interrupts is under execution, other interrupts should not be invoked. This is performed in a system in different ways. The problem of infinite loop occurs due to successive interruptions of the active intar signals. These are three mechanisms to solve problem of infinite loop. Processor should ignore the interrupts until execution of first instruction of ISR. Processor should automatically disable interrupts before starting the execution of the ISR. Processor has a special intar line for which the interrupt handling circuit interrupt and circuit responds only to the leading edge of the signal. Such line is called the edge triggered. Sequence of events involved in handling the interrupt requests. The device raises an interrupt request. The processor interrupts the program currently being executed. Interrupt are disabled by changing the control bits in the process status register. PS. The device is informed that its request has been recognized, and in response, the device deactivates the interrupt request signals. The action requested by the interrupt is performed by the interrupt service routine. Interrupts are enabled and execution of the interrupted program is resumed. Handling multiple devices. While handling multiple devices, the issues are concerned. How can the processor recognize the device requesting an interrupt? How can the processor obtain the starting address of the appropriate ISR? Should a device be allowed to interrupt the processor while another interrupt is being serviced? How should two or more simultaneous interrupts requests be handled? Vectored interrupt. A device requesting an interrupt identifies itself by sending a special code to processor over bus. Then the processor starts executing the ISRs. The special code indicates starting address of the ISR. The special code length ranges from 4 to 8 bits. The location pointed to by the interrupting device is used to store the starting address of the processor. The starting address of the ISR is called the interrupt vector. Processor loads interrupt vector into PC and executes appropriate ISR. When processor is ready to receive interrupt vector code, it activates int A, this interrupt acknowledgement line. Then IO device responds by the sending its interrupt vector code, turning off the interrupt signal. The interrupt vector also includes a new value for the processor status register. Interrupt nesting. A multiple priority schema is implemented by using separate intar and int A lines for each device. Interrupt nesting. Each intar line is assigned a different priority level as shown in the figure. Device int A, int R1, int A. Then device 2 to device B, int B, then each device has a separate interrupt request and interrupt acknowledge line. Each interrupt request line is assigned a different priority level. Interrupt requests received over these lines are sent to priority arbitration circuit in the processor. If the interrupt request has a higher priority level than the priority of the processor, then the request is accepted. Priority level of the processor is the priority of program that is currently being executed. Processor accepts interrupts only from devices that have higher priority than its own. At the time of execution of ISR for some device, priority of processor is raised to that of the device. Thus, interrupts from devices at the same level of priority or lower are disabled. Privileged instruction processor's priority is encoded in a few bits of PS word. PS processor status. Encoded bits can be changed by privileged instruction that write into PS. Privileged instructions can be executed only while processor is running in supervisor mode. Processor is in supervisor mode only when executing operating system routines. Privileged exception: user program cannot accidentally or intentionally change the priority of the processor and disrupt the system operation. An attempt to execute a privileged instruction while in user mode leads to the privileged exception. Simultaneous request daisy chain. A daisy chain with multiple priority levels is as shown in the figure. The interrupt request line entire is common to all devices as shown in the figure. The interrupt acknowledgement line is connected in a daisy fashion as shown in the figure. The signal propagates serially from one device to another. The several devices raise an interrupt by activating int R signal. In response to the signal, processor transfers its device by activating the int A signal. This signal is received by device 1. This device 1 blocks the propagation of int A signal to device 2 when it needs processor service. Device 1 transfers the int A signal to next device when it does not require the processor service. In daisy chain arrangement, device 1 has the higher priority advantage. It requires fewer wires than the individual connections. Arrangement of priority groups. Processor priority arbitration. Int R1, then int RP, device, int A1, int AP will be the priority arbitration circuit. In this technique, devices are organized in a group of, and each group is connected to the processor at a different priority level. Within a group, devices are connected in a daisy chain fashion as shown in the figure. Direct memory access. It's a process of transferring the block of data at high speed in between main memory and external device I/O without continuous intervention of the CPU. It's called DMA. A DMA operation is performed by one control circuit and is part of the I/O interface. The control circuit is called DMA controller, hence DMA transfers operation is performed by DMA controller. To initiate directed data transfer between main memory and the external devices, DMA controller needs parameters from the CPU. These three parameters are starting address of the memory block, number of words to be transferred, types of operation, read or write. Starting address of the memory block, number of words to be transferred, type of operation, read or write. After receiving these three parameters from CPU, DMA controller establishes directed data transfer operation between main memory and external devices without the involvement of CPU. Register of DMA controller consists of three types of registers. Starting address register. The format of the starting address register is as shown in the figure. It is used to store the starting address of the memory block. Starting address. Word count register. The format of the word count register is as shown in the figure. It is used to store the number of words to be transferred from main memory to the external devices and vice versa, word count. Status and controller register. The format of the status and controller register is as shown in the figure. Status and control IRQ, IE, R or W, 1 or 0, done. Interrupt request Q is 30. Then done bit. The DMA controller sets its bit to 1 when it completes the direct data transfer data between main memory and the external devices. This information is informed to CPU by means of done bit. RW read or write operation. This bit is used to differentiate between memory read or memory write operation. The read or write, 1 for read operation and 0 for write operation. When this bit is set to 1, DMA controller transfer one block of data from external device to main memory. And this bit is 0, set to 0. DMA controller transfers the one block of data from main memory to external memory, i.e. interrupt enable bit. The DMA controller enables the interrupt enable bit after the completion of the DMA operation. Interrupt request IRQ. The DMA controller requests the CPU to transfer new block of data from source to destination by activating this bit. The computer with DMA controller is shown in the figure. Processor, main memory, system bus, disk, DMA controller, printer, keyboard, disk, DMA controller, disk, DMA controller, network interface. The DMA controller connects to external devices, namely disk 1 and disk 2, to the system bus as shown in the figure. The DMA controller also interconnects high-speed network devices to system bus as shown in the figure. Let us consider a direct data transfer operation by means of DMA controller without the involvement of the CPU in between memory and the disk 1 and indicated by dotted lines in the figure. To establish direct data transfer operation between the main memory and the disk, DMA controller requests the processor to obtain three parameters, namely starting address of the memory block, number of words to be transferred, type of the operation, read or write. After receiving these three parameters from the processor, DMA controller directly transfers block of data main memory and the external memory disk 1. This information is informed to CPU by setting respective bits in the status and control register of the DMA controller. These are two types of requests with respect to system bus: CPU request, DMA request. Highest priority will be given to DMA request. Actually, the CPU generates memory cycles to perform read and write operations. The DMA controller steals memory cycles from the CPU to perform read and write operations. This approach is called cycle stealing. An exclusive option will be given to DMA controller to transfer block of data from external devices to main memory and from main memory to external devices. This technique is called burst mode of operation. An exclusive option will be given to the DMA controller to transfer block of data from external devices to main memory and from main memory to external device. This technique is called burst mode of operation. Bus arbitration. Any device which initiates data transfer operation on the bus at any instant at a time is called bus master. When the bus mastership is transferred from one device to another device, the next device is ready to obtain the bus mastership. The bus mastership is transferred from one device to another based on the principle of priority system. There are two types of bus arbitration technique. Centralized arbitration. In this technique, CPU acts as a bus master, or any control unit connected to bus can act as a bus master. Here the processor BBSY, BR, DMA controller 1, DMA controller 2, BG1, BG2, BBSY, BR. What are they? Let's see now. The schematic diagram of the centralized bus arbitration is as shown in the figure. The following steps are necessary to transfer the bus mastership from CPU to one of the DMA controller. The DMA controller requests the processor to obtain the bus mastership by activating the BR bus request signal. In response to this signal, CPU transfers the bus mastership to the requested device's DMA controller 1 in the form of BG bus grant. When the bus mastership is obtained from the CPU, the DMA controller 1 blocks the propagation of bus grant signal from one device to another device. The BG signal is connected to DMA controller 2 from DMA controller 1 and as daisy fashion style and as shown in the figure. When the DMA controller 1 has not sent BR request, transfer the bus mastership to DMA controller 2 by unblocking bus grant signal. When the DMA controller 1 receives the bus grant signal, it blocks the signal from passing to DMA controller 2 enables BBSY signal. When BBSY signal is set to 1, the set of devices connected to system bus doesn't have any rights to obtain the bus mastership from the CPU. Distributed bus arbitration. In this technique, two or more devices trying to access system bus at the same time may participate in bus arbitration process. The schematic diagram for distributed bus arbitration is as shown in the figure. Start arbiter R1, R0 to R3, then it is connected to voltages, then NOT gates 01, 010, 111, OC. Interface circuit for a device A. The external device requests the processor to obtain bus mastership by enabling start arbitration signal. In this technique, 4-bit code is assigned to each device to request the CPU in order to obtain bus mastership. Two or more devices request the bus by placing 4-bit code over the system bus. The signals on the bus interrupt the 4-bit code and produces winner as a result from the CPU. When the input to the one driver equals to 1 and the input to the another driver equals to 0 on the same bus line, this state is called as low level voltage state of bus. Consider two devices, namely A and B, trying to access bus mastership at the same time. Let assign the code for devices A and B are 50101 and 60110 respectively. The device A sends the pattern 0101 and the device B sends its pattern 0110 to master. The signals on the system bus interpret the 4-bit code for devices A and B, produces devices B as a winner. The device B can obtain the bus mastership to initiate direct data transfer between the external and main memory. Memory system, speed, size and cost. The block diagram of memory hierarchy is as shown in the figure below. Processor registers primary cache L1, secondary cache L2, main memory, magnetic disk, secondary memory, increasing size, increasing speed, increasing cost per bit, cache SRAM, main memory, DRAM, L1 cache on processor, L2 cache off processor. Registers. The fastest access is to data held in registers, hence registers are part of the memory hierarchy. More speed, small size and cost per bit is also more. At the next level of hierarchy, small amount of memory can be directly implemented on the processor chip. This memory is called as processor cache. It holds the copy of recently accessed data and instructions. There are two levels of caches, with level 1 and level 2. Level 1 cache is part of the processor. Level 2 cache is the placed in between the level 1 cache and main memory. The level 2 cache is implemented using SRAM chips. The next level in the memory hierarchy is called as main memory. It is implemented using dynamic memory components DRAM. The main memory is larger but slower than cache memory. The access time for main memory is 10 times longer than the cache memory. The level next in the memory hierarchy is called as secondary memory. It holds huge amount of data. Characteristics: speed, size, cost, SRAM, DRAM, magnetic disk. Very fast, slower than RAM. Large size SRAM, small. SRAM is expensive, less expensive, and it is even more less expensive. Memory, speed, size, registers, primary cache, secondary cache, main memory, secondary memory. Very high, low, lower than secondary memory, very low. Size is lowest. The main memory is built with DRAM, DRAM. SRAMs are used in cache memory where speed is essential. The cache memory is of two types: primary processor cache, level 1 or L1 cache. It is always located on the processor chip. Secondary cache, level 2 or L2 cache. The memory is implemented using the dynamic components SIMM, DIMM. The access time for main memory is about 10 times longer than the access time for L1 cache. Cache memory: it is the fast access memory located in between processor and main memory. Processor, cache memory, main memory, as shown in the figure. It is designed to reduce the access time. The cache memory holds the copy of recently accessed data and instruction. The processor needs less access time to read the data and instruction from the cache memory as compared to main memory. Hence, by incorporating cache memory in between processor and main memory, it is possible to enhance the performance of the system. The effectiveness of cache mechanism is based on the property of locality of reference. Locality of reference: many instructions in the localized areas of the program are executed repeatedly during some time of execution. Remainder of the program is accessed relatively infrequently. There are two types of locality reference: temporal. The recently executed instructions are likely to be executed again and again. Example: instructions in loop, nested loops, and few function calls. Spatial: instructions in close proximity to recently executed instructions are likely to be executed soon. Nearby instructions: if active segment of program is placed in cache memory, then total execution time can be reduced. Cache block, cache line refers to the set of contiguous address locations of some size. This number of blocks is small compared to the total number of blocks available in main memory. Corresponding between main memory block and cache memory block is specified by mapping functions. If the cache memory is full, one of the blocks should be removed to create space for the new block. This is decided by cache control hardware. The collection of rules for selecting the block to be removed is called the replacement algorithm. The cache control unit determines whether the requested word currently exists in the cache. If data is available for read operation, the data is read from cache. The write operation, writing to memory, is done in two ways: write through protocol and write back protocol. Write through protocol, here the cache location and the main memory location are updated simultaneously. Write back protocol, this technique is to update only the cache location and mark the cache location with a flag bit called dirty modified bit. The word in memory will be updated later when the marked block is removed from cache. During read operation, if the requested word currently doesn't exist in the cache, then read miss will occur. To overcome the read miss, load through early restart protocol is used. Load through protocol, the block of words that contains the requested word is copied from the memory into cache. After the entire block is loaded into cache, the requested word is forwarded. During write operation, if the requested word does not exist in the cache, the write miss will occur. If write through protocol is used, the information written directly into the main memory. If write back protocol is used, then block containing the addressed word is first brought into the cache, then the desired word in the cache is overwritten with the new information. Mapping functions. There are three techniques to map main memory blocks into cache memory: direct mapped cache, associative mapping, set associative mapping. Direct mapping, the simplest way to determine cache locations in which to store memory blocks, is the direct mapping technique, is as shown in the figure. Cache block number is block J of main memory percentage modulo 128. If there are 128 blocks in a cache, then block J of the main memory maps onto block J modulo 128 of the cache. When the memory blocks of 0, 128 and 256 are loaded into cache, the block is stored in cache block 0. Similarly, memory blocks 129 stored in a cache block 1, 1 modulo 128, 1. 129 mod 128 is also equal to 1. The contention may arise even when the cache is full, but more than one memory block is mapped to given cache block position. The contention is resolved by allowing the new blocks to override the currently resident block. Memory address determines the placement of the block in the cache. Main memory block 0, block 1 till some number. Cache tag block 0 to block 127 tag. Main memory block has to be placed in the particular cache block number by using the formula cache block number is equals to main block number modulo number of blocks present in the cache memory. Then, for example, main memory block number is 129, has to be placed cache block number 1 by using the formula 129 modulo 128, that is remainder is 1. Then 258 by 128 as remainder is 2. Main memory block 258 has to be placed in the cache block 2. Main memory address will be tag block word. Tag block word. The main memory block is loaded into cache block by means of memory address. The main memory address consists of three fields. As shown in the figure, each block consists of 16 words, hence least significant 4 bits are used to select one of the 16 words. The 7 bits of memory address are used to specify the position of the cache block location. The most significant 5 bits of memory address are used stored in the tag bits. The tag bits are used to map one of the 2 per 5 32 blocks into cache block location. The higher order 5 bits of memory address are compared with the tag bits associated with the cache location. If they match, then the desired word is in the block of the cache. If there is no match, then the block containing the required word must first be read from the main memory and loaded into the cache. It is very easy to implement but not flexible. Associative mapping, it is also called as associative mapped cache. It is much more flexible. In this technique, main memory block can be placed into any cache block position. In this case, 12 tag bits are required to identify a memory block when it is resident of the cache memory. Any cache block position. 12 tag bits are required to identify a memory block that is resident of the cache memory. The associative mapping technique is illustrated as shown in the figure. Tag cache block 0 to block 127, same thing. Main memory is there, but tag and the word. Associative mapping. In this technique, 12 bits of address generated by the processor are compared with the tag bits of each block of the cache to see if the desired block is present. This is called associative mapping technique. Set associative mapping. It is the combination of direct and associative mapping techniques. The blocks of cache are divided into several groups. Such groups are called sets. Each set consists of the number of cache block. The memory block is loaded into one of the cache sets. The main memory address consists of three fields such as shown in the figure. The lower 4 bits of the memory address are used to select a word from a 16 words. The cache consists of 64 sets as shown in the figure, and 6-bit field is used to select a cache set from 64 sets. As there are 64 sets, the memory is divided into groups containing 64 blocks, where each group is given a tag number. The most significant 6 bits of memory address is compared with the tag fields of each set to determine whether memory block is available or not. The following figure clearly describes the working principle of set associative mapping technique. Cache that has k blocks per set is called the k-way set associative cache. Each block contains a control bit called valid bit. A valid bit indicates that whether the block contains valid data, updated data. A dirty bit indicates that whether the block has been modified during its cache residency. Valid bit is 0 when power is initially applied to system. Valid bit is 1 when the block is loaded from the main memory at the first time. If the main memory block is updated by a source, if the block in the sources already exists in the cache, then the valid will be 0. If the processor and the DMA uses the same copies data, then it is called as cache coherence problem. Contention problem of direct mapping is solved by having few choices for block placement. The hardware cost is decreased by reducing the size of the associative search. Set 0, set 1, set 63. Tag set words. Tag set words 4095. Thank you for watching. Do like, share, and subscribe to my channel.